Section: Introduction. In this section, we discuss the importance of embodied thinking and reasoning in robotics. We recognize that reasoning helps us act with intention, as we subconsciously consider context, goals, and constraints before taking action. For robots to operate effectively, they need to learn to reason, not just map images and instructions to commands. While large language and vision models have made significant progress, robotics has not kept pace. Vision language action models aim to give robots similar capabilities, but they still struggle with flexibility and robustness. Current models are often brittle and lack transparency, making it hard to understand their decision-making processes. This issue arises from limited data and a lack of structured learning, as robotics requires detailed, embodied interaction data, which is challenging to obtain. We believe that robotics can benefit from structured learning, similar to recent advancements in language models. We introduce MolmoAct, a family of open action reasoning models that integrate perception, planning, and control through a structured reasoning process. MolmoAct interprets language instructions, senses its environment, generates spatial plans, and executes them as smooth actions. The model encodes observations and instructions into structured representations, which guide the prediction of robot actions. This three-stage reasoning architecture allows MolmoAct to produce explainable and controllable behavior. Our model outperforms competitive baselines on standard benchmarks and adapts well to new tasks with efficient fine-tuning. It also generalizes effectively to various environments and task changes, providing clear insights into its decision-making. MolmoAct is fully open source, including model weights, training code, and components of our multimodal reasoning dataset. We aim for it to serve as a foundation for building agents that can reason and transform perception into purposeful action. MolmoAct builds on the Molmo framework, reusing its vision language backbone and extending its capabilities to generate structured action sequences. It is trained on a subset of the OpenX embodiment mixture and augmented with a new dataset. In the following sections, we will detail our methods for tokenizing actions, transforming vision language actions into an action reasoning model, and enabling action steerability through visual reasoning traces. To equip our action model with visual and linguistic knowledge, we utilize vision language models, which typically consist of a visual encoder, a projection module, and a large language model. Our work builds on Molmo, which follows this structure. We use various vision encoders and language models, ensuring that we initialize components from open checkpoints when possible. This approach allows for reproducibility and supports community-driven research. Section Summary. In this section, we introduce MolmoAct, an open-source action reasoning model that integrates perception, planning, and control to enable robots to reason and execute actions based on language instructions. By utilizing a structured reasoning pipeline and fine-tuning on specialized datasets, MolmoAct demonstrates superior performance, adaptability, and explainability compared to existing models in robotic manipulation tasks. Section: Vision Language Action Model. In this section, we discuss our Vision Language Action Model, VLM. A standalone VLM, even with expert prompting, cannot directly control a robot because it lacks an understanding of the robot's actions and dynamics. It can only offer high-level plans based on current observations. To create precise commands, we treat action prediction as a task of modeling sequences of vision and language. For each action dimension, we normalize the data using quantiles from our dataset and divide it into 256 equal-width bins between the 1st and 99th percentiles. This approach minimizes the impact of outliers while maintaining useful detail, resulting in a 12-dimensional action represented as 12 integers. We train the model end-to-end with a focus on predicting the next token, calculating loss only on the action tokens. Previous methods used distinct language tokens for the 256 action bins, but these tokens lack the necessary relationships. To address this, we use a more suitable method that respects the structure of the action space. We select the last 256 tokens from the Quen2 tokenizer and utilize their underlying byte-level symbols, which are naturally ordered. We then assign these tokens to the 256 bins in a way that keeps adjacent bins linked to adjacent symbols, forming our action token vocabulary. This method provides a smoother starting point for optimization and significantly cuts down training time. For instance, while the GR00TN1 model required 50,000 GPU hours, our MolmoAct model only needed 9,216 GPU hours, which is 5.4 times less. Next, we introduce our action reasoning model. We recognize that chain of thought, COT, has improved the performance of language models on complex tasks, and we apply a similar approach to multimodal language models, MLLMs, using multimodal chain of thought, MCOT, for better handling of long multimodal contexts. However, this reasoning approach is often missing in robotic control policies. While some efforts have been made to integrate reasoning into vision language actions, VLAS, they typically focus on high-level plans or object-centric cues, neglecting essential elements like depth perception and detailed motion plans. Our goal is to enable the model to explicitly reason about depth and create a clear motion plan before executing actions. In MolmoAct, we incorporate intermediate reasoning not just through language but by teaching our models to reason spatially. We frame visuomotor control as a sequence modeling task that includes action COT for spatial reasoning. Based on images and instructions, our autoregressive action reasoning model first generates a brief sequence of depth perception tokens that summarize the depth of the current observation, followed by a visual reasoning trace of the intended motion, and finally produces the action tokens for the next control step. This process is similar to textual COT, but with action COT, each step is grounded in space. Depth perception is crucial for understanding space and predicting robot actions. Traditional VLMs and VLAS often rely solely on RGB images and text instructions, which can hinder performance in tasks requiring strong spatial understanding. Previous research has shown that depth perception tokens enhance reasoning for visual spatial tasks. Building on this, we integrate depth token prediction into our action reasoning, improving robot control in 3D environments. We define an auxiliary vocabulary for depth perception tokens. For each input image, we establish a target depth string, which is indexed in a codebook created by a pre-trained depth estimator. This codebook quantizes dense depth maps into a fixed-length sequence of indices, with a clear one-to-one mapping between each index and a depth token. We use a distillation strategy to ground our depth perception tokens. The specialist generates the ground truth depth string, and the VLA learns to predict this string from the original RGB observation, thereby internalizing depth for better trajectory and action generation. Section Summary. In this section, we describe our vision language action model, MolmoAct, which enhances robot control by integrating depth perception and spatial reasoning into action prediction, allowing for more accurate and efficient command generation. We utilize a novel approach to represent action tokens and depth perception, significantly reducing training time while improving the model's ability to understand and execute complex tasks in 3D environments. Section: Visual Reasoning Trace. In this section, we discuss our approach to planning for robots. We believe that planning ahead is essential for task completion. Instead of using text descriptions, we opt to plan based on the trajectory of the robot's end effector as it appears in the image. This method provides a clearer and more accurate representation of how the robot should move from its current position to complete the task. For a given image, we define the end effector visual reasoning trace as a series of points that form a polyline. This polyline consists of 26 points, representing the robot's movement from the current observation to future frames. Each point's coordinates are adjusted to fit the image dimensions, with one point indicating the current position of the end effector and the others showing its future locations. We evenly select points from the future frames to create the full polyline. Next, we describe our action reasoning procedure. Using depth perception tokens and the visual reasoning trace, our model, MolmoAct, can perform action reasoning in space. Given an RGB image and a language instruction that includes an action prompt, we generate 3 sequences of tokens in order. First, depth perception tokens. Second, the visual reasoning trace. And finally, action tokens. Each stage builds on the previous one, ensuring that the final actions are grounded in both the inferred depth and the planned movement. We define steerability as the ability to guide the robot's actions based on user instructions. Previous systems have relied solely on language for steering, which presents challenges such as the need for extensive language action pairs, ambiguity in natural language, and the tendency of models to become rigid with phrasing. To address these issues, we allow users to draw a visual reasoning trace directly on the camera image to indicate the desired path for the end effector. This trace is clear, easily adjustable, and applicable across various tasks without needing extensive text action datasets. During testing, we combine the RGB image, user instruction, and drawn trace to generate the next action tokens, enabling precise control that adapts to user input. Regarding data curation and generation, we train MolmoAct on a variety of datasets. In the pre-training phase, we utilize multimodal web data, auxiliary robot data, and action reasoning data. We also collect and train with the MolmoAct dataset during the mid-training stage. For action reasoning data, we frame visuomotor control as a sequence modeling problem enhanced with an action chain of thought. This allows us to transform any standard robot action dataset into action reasoning data by adding predicted depth perception tokens and visual reasoning traces to the action tokens, based on both language and robot observations. Each robot episode consists of a series of time steps, where each time step includes an RGB image, a language instruction, and a corresponding action. To convert any robot data into our action reasoning format, we generate ground truth depth perception tokens and visual reasoning traces for each time step, which we will detail further. Section Summary. In this section, we describe our approach to robot task planning using a visual reasoning trace, which represents the robot's end effector trajectory in an image, allowing for precise movement guidance. We also outline our action reasoning procedure that combines depth perception tokens and visual traces to enable robust, user-steered control, addressing the limitations of language-only steering by allowing users to draw desired paths directly on images. Section: Depth Perception Tokens. In this section, we describe how we generate depth perception tokens for each frame of a demonstration. We begin by training a VQVAE on 10 million depth maps from tabletop manipulation images sourced from the RT1, Bridge Data V2, and BCZ datasets. We utilize Depth Anything V2 to create a depth map for each RGB observation image. The VQVAE is trained to minimize the difference between the input RGB images and their corresponding depth maps over 20 epochs. After training, we encode each observation image to obtain latent embeddings, which we represent using a learned codebook of 128 dimensions that maps directly to depth tokens. All images are resized to a specific resolution during training and inference to ensure we represent 100 tokens per image. This allows us to express the depth map of each observation image as a string of 100 tokens, which we use for labeling our depth perception tokens. Next, we generate visual reasoning traces for each frame using MolmoAct, a vision language model trained on various 2D pointing datasets. For each time step, we extract the pixel coordinates of the robot's gripper and compile these across the episode to create a visual reasoning trace. We prompt MolmoAct with instructions to point to the robot gripper, adjusting for single-arm or bimanual robots. MolmoAct provides 2D coordinates for the predicted gripper location, which we rescale. By applying this query at every time step, we obtain one gripper location per frame, linking these predictions to form a complete trajectory. For bimanual robots, we issue separate prompts for each gripper. We construct a visual reasoning trace by selecting points from the current to the final point, including up to 3 evenly spaced intermediate points, resulting in a trace of 1 to 5 points that represent the end effector's future motion. To enhance MolmoAct's spatial reasoning, we extend our data generation pipeline to create 3 auxiliary supervision datasets. I. Auxiliary depth data, where the model predicts the target depth perception token sequence from an RGB observation and language instruction. E. Auxiliary trace data, where the model predicts the corresponding visual reasoning trace. And E. Trajectory conditioned action data, where the model predicts the next action based on the current image, instruction, and ground truth visual reasoning trace. We primarily curate the trajectory conditioned action data to enable the steerability feature of MolmoAct. After generating ground truth labels for each frame, we align the depth perception tokens, visual reasoning trace, and actions for instruction tuning. We also introduce the MolmoAct dataset to enhance the model's manipulation performance and spatial reasoning in real household settings. This dataset comprises 10,689 high-quality trajectories of a single-arm Franka robot executing 93 unique manipulation tasks in home and tabletop environments. Each trajectory averages 112 time steps, collected over 2 months by 5 operators following strict protocols. For home environment data, we mounted the Franka robot on a mobile platform to capture diverse scenes across various rooms. Each task reflects a specific household chore, with long horizon tasks broken down into subtasks to help the model learn individual skills before combining them into complex behaviors. We collected 7,730 trajectories across 73 distinct tasks and 20 verbs. For tabletop data, we gathered 2,959 trajectories covering 20 atomic tasks, each performed with various objects to enhance robustness and generalization. Each task was decomposed into atomic motions, and we collected data for each motion, such as opening, picking, flipping, putting, and closing, to create a comprehensive set of motion primitives. Section Summary. In this section, we describe our process for generating depth perception tokens and visual reasoning traces using a trained VQVAE on depth maps and a vision language model, respectively. We also outline the creation of the MolmoAct dataset, which includes 10,689 trajectories of a Franka robot performing various manipulation tasks in home and tabletop environments, aimed at enhancing spatial reasoning and manipulation performance. Section: Multimodal Web Data. In this section, we discuss our approach to using multimodal web data. Previous research has indicated that training vision language agents, VLAS, with a mix of data from vision language models, VLMs, results in policies that are more adaptable. These policies show greater resilience to changes in lighting and backgrounds and perform better in unfamiliar settings and with new objects. We incorporate a variety of multimodal web data from Molmo's supervised fine-tuning phase, which includes several academic datasets aimed at enhancing general visual skills, as well as PixMo for detailed understanding and pointing tasks. Additionally, we utilize LVIS to help the model predict the center of bounding boxes for specific categories, linking language to image regions. For our training process, we first pre-train MolmoAct using action reasoning data from a subset of the OXE dataset, along with auxiliary robot data and multimodal web data. We then mid-train the model on the MolmoAct dataset before fine-tuning it for specific tasks. During pre-training, we mix action reasoning data, auxiliary robot data, and multimodal web data. The robot data comes from a subset of OXE, including RT1, Bridge Data V2, and BCZ, totaling 10.5 million samples, which we convert into action reasoning data. We also include atomic depth, trace, and trajectory conditioned action data, co-training with 2 million samples of multimodal web data. The sampling rates for these datasets are defined, and the total pre-training data amounts to 26.3 million samples. We use 256 H100 GPS for training, completing 100,000 gradient steps with a batch size of 512, which requires 9,728 GPU hours. After pre-training, we enter the mid-training phase, focusing on high-quality action reasoning data relevant to household tasks. We create the MolmoAct dataset with 1 million action reasoning samples and another million auxiliary trajectory condition samples, which we find helpful for enhancing performance. Each sample consists of 2 side-mounted camera views and 1 wrist camera view, which we pair for training. We fine-tune the model on this dataset for 50,000 gradient steps with a batch size of 128, using 128H100 GPS over 2,304 GPU hours. In the final post-training stage, we adapt the model to new tasks by collecting a small number of tele-operated demonstrations. We generate perception and visual reasoning tokens for each demonstration, converting them into action reasoning and trajectory condition data. To improve manipulation performance, we implement action chunking, formatting action predictions into fixed-length segments. We fine-tune MolmoAct for single or multi-tasks using parameter-efficient LoRa fine-tuning, maintaining a fixed LoRa rank and alpha to retain pre-trained capabilities. We adjust batch sizes based on the task and apply consistent training configurations across all evaluations. Further details can be found in Appendix B. Section Summary. In this section, we describe the training process of MolmoAct, which involves pre-training on a diverse mixture of action reasoning, auxiliary robot, and multimodal web data to enhance generalization and robustness, followed by mid-training on high-quality action reasoning data for household manipulation, and finally post-training to adapt the model to new tasks using tele-operated demonstrations and action chunking techniques. Our approach leverages a total of 26.3 million samples across various datasets to optimize performance and adaptability in real-world scenarios. Section: Experimental Evaluation. In this section, we present our experimental evaluation, which includes a variety of studies to thoroughly test MolmoAct against strong baseline models. We evaluate the MolmoAct 7BD version in 3 main areas: I. Its initial capabilities right after pre-training, E. Its ability to adapt to different tasks and robotic forms after training, and E. Its interactive features as an action reasoning model with the MolmoAct 7BD pre-trained version. To answer our research questions, we conduct tests in both simulated and real-world environments. We first assess how well MolmoAct performs on tasks similar to its training data by comparing it to other models using the simpler ENV benchmark. Next, we explore how effectively MolmoAct can adapt to new tasks through lightweight fine-tuning, using the Libero simulation suite for benchmarking. We also validate its performance in real-world scenarios with 2 different robotic setups, a single arm and a bimanual arm. We investigate how well MolmoAct can generalize beyond its training data through out-of-distribution tests and variant aggregation experiments. Additionally, we examine how mid-training on the MolmoAct dataset enhances its overall performance through ablation studies. We also evaluate how well MolmoAct follows language commands by comparing it to other models in an open-ended simulation where human evaluators provide prompts. Lastly, we analyze how steerable MolmoAct is and how this feature can improve user interactions by guiding it with trajectory cues and studying the resulting dynamics. For our evaluation setup, we first tested MolmoAct in a zero-shot manner, right after pre-training and before any specific fine-tuning. Unlike other models that rely on large private datasets, MolmoAct was trained on a curated selection of action reasoning data, totaling about 26.3 million data points, which is significantly smaller than the datasets used by other models. We used the simpler ENV benchmark to evaluate its generalization capabilities, focusing on visual matching tasks aligned with its training distribution. MolmoAct achieved a strong zero-shot performance, reaching 70.5% accuracy on the simpler ENV visual matching tasks, outperforming several baseline models. After fine-tuning on a specific subset of data, its accuracy improved to 71.6%, indicating that MolmoAct is effective both as a zero-shot generalist and as a strong starting point for fine-tuning. In terms of fine-tuning efficiency, we evaluated MolmoAct in both simulated and real-world settings. In simulation, we followed the OpenVLA protocol and tested it on the Libero benchmark, which includes various robotic manipulation tasks. We fine-tuned MolmoAct using low-rank adaptation and compared it to other state-of-the-art models. In the real world, we assessed its performance on 6 tasks with both single-arm and bimanual setups, using human demonstrations for evaluation. Our results on the Libero benchmark showed that MolmoAct achieved an average success rate of 86.6%, the highest among all models tested. It performed particularly well on the long-horizon tasks, surpassing the second-best method by a significant margin. In real-world evaluations, MolmoAct demonstrated effective fine-tuning and generalization, outperforming other models in task progression across both single-arm and bimanual tasks. Section Summary. In this section, we rigorously evaluate MolmoAct through various benchmarks, assessing its pre-training capabilities, adaptability to new tasks, and performance in real-world scenarios. Our results show that MolmoAct excels in zero-shot tasks, achieves high accuracy after fine-tuning, and demonstrates strong generalization across different robotic embodiments, outperforming several state-of-the-art models. Section: Effectiveness of MolmoAct in out-of-distribution generalization. In this section, we evaluate the effectiveness of MolmoAct in generalizing beyond the training data in both simulated and real-world environments, focusing on zero-shot and fine-tuned scenarios. In our simulations, we use a specific protocol that introduces changes in lighting, textures, and camera angles to create distribution shifts. We compare MolmoAct with several leading generalist policies, including TraceVLA, RT1X, OpenVLA, RoboVLM, MolmoAct, 1 FAST, and Spatial Val. For the real-world tests, we utilize a single Franca arm in a multitask setup with 3 objects and 2 differently colored plates on a table. We gather over 300 demonstrations across 3 task types and then train MolmoAct alongside the baseline models in a multitask context. During our evaluation, we assess generalization across 4 areas. 1. Language variation, which involves rephrased instructions. 2. Spatial variation, where we change the positions of target objects. 3. Distractors, which includes adding irrelevant objects. And 4. Novel objects, where we replace target objects with ones that have not been seen before. We benchmark MolmoAct against 1 FAST and OpenVLA, testing 3 variations for each task and conducting 4 trials for each variation. In our evaluation results, we find that in simulations, the fine-tuned MolmoAct achieves a score of 72.1% on the variant aggregation tasks, outperforming all baseline models and exceeding the second-best model, RT2X, by 7.8%. The performance difference between variant aggregation and visual matching is minimal, indicating MolmoAct's robustness to visual and distributional changes. In real-world tests, MolmoAct consistently outperforms all baselines across all generalization areas, achieving an average improvement of 23.3% in task progression over 1 FAST. Next, we assess the impact of mid-training with the MolmoAct dataset through real-world experiments on 3 curated tasks: close_lid, rotate_pot, and pour_t. For each task, we collect 50 demonstrations and train 4 models: MolmoAct7BD, MolmoAct7BD without mid-training, 1 FAST, and OpenVLA. Each model is evaluated over 10 trials per task. Our results show that MolmoAct outperforms the version without mid-training by an average of 5.5% across the 3 tasks, indicating that mid-training on the MolmoAct dataset provides a consistent performance boost. Even without mid-training, MolmoAct surpasses one FAST and OpenVLA by 14.8% and 10.9%, respectively. We also evaluate MolmoAct's ability to follow natural language instructions in two scenarios: executing open-ended commands in simulation and generating visual traces based on language prompts. In the simulation, we create 5 manipulation scenarios using a Google robot, each involving new out-of-distribution objects. 10 participants provide 29 open-ended instructions, and we compare MolmoAct to Spatial VLA and OpenVLA, both pre-trained on the OXE dataset. For each instruction, the models generate trajectory rollouts, which are evaluated by human annotators who select the best match. We collect over 1,500 votes, which we convert into ELO ratings. For visual trace generation, 10 participants write 87 language prompts based on 30 images from the internet. We evaluate MolmoAct against GEMINI 2.5 Flash, GPT-4o, and Hamster, a model fine-tuned for trace generation. Participants vote in a similar blind evaluation, resulting in over 1,000 votes. In our evaluation results, MolmoAct achieves the highest ELO rating in the simulation instruction following task, outperforming Spatial VLA by 109 points and OpenVLA by an even larger margin. Pairwise win rates show that MolmoAct wins 58% of comparisons against Spatial VLA and 81% against OpenVLA. In the visual trace task, MolmoAct again outperforms all baselines, achieving significantly higher ELO scores with non-overlapping confidence intervals, demonstrating strong generalization in both spatial execution and language-grounded reasoning. Section Summary. In this section, we evaluate the effectiveness of MolmoAct in out-of-distribution generalization through both simulation and real-world tasks, demonstrating its superior performance over state-of-the-art policies in various generalization scenarios. Our results show that MolmoAct consistently outperforms baselines, achieving significant improvements in task execution and instruction following, particularly when mid-training with the MolmoAct dataset is applied. Section: Steerability of MolmoAct. In this section, we evaluate MolmoAct's capability to guide robot actions, especially when initial language instructions are unclear. We focus on how different interaction methods help MolmoAct reach user-defined targets during tasks. To do this, we created a task called Pick Up the Bull, training MolmoAct and a baseline model, 1 FAST, using 100 demonstrations. Each demonstration included 2 different language instructions, one for a clean bowl and another for a dirty bowl, as shown in Figure 7. During our evaluation, we first gave ambiguous instructions like, pick up the bowl, which led MolmoAct to predict a path toward one of the bowls. We then tested 2 steering methods, using visual sketches to guide the model to the other bowl and providing open-ended language instructions from participants. We also tried to steer 1 FAST by changing its language instructions during testing. Each model underwent 15 trials, and we assessed their performance based on task progression. From our experiments, we found that MolmoAct is significantly more responsive to visual inputs, achieving a success rate of 75%. Steering with visual traces outperformed steering with open-ended language instructions by 33%. Furthermore, MolmoAct demonstrated better instruction following abilities than 1 FAST, exceeding its performance by 29%, which shows its improved responsiveness to user commands. In the realm of generalist robot manipulation, recent developments have moved from training robots for specific tasks to using large, varied datasets that cover many scenarios. This change has led to models that not only perform well in their training environments but also adapt to new scenes, tasks, and objects. Much of this progress is driven by large language models and vision language models, which have given rise to vision language action models. These models pre-train on extensive web data to gain a deep understanding of the world and then fine-tune for robot control. While many share similar foundational models, they differ in how they handle actions, using various techniques for action representation. A significant challenge for these models is their dependence on large amounts of robotics-specific data, often gathered through teleoperation. In contrast, MolmoAct seeks to utilize spatial reasoning to train an action reasoning model that can perform competitively with much less data. We also note that enhancing robotic policies with high-level reasoning, by integrating LLMs or VLMs, can greatly improve performance on complex tasks. Some research has focused on separating perception and reasoning from low-level control, allowing VLMs to generate task plans or spatial layouts, while a different control module executes these plans. MolmoAct can be steered through both natural language and an interactive visual sketch interface, which enhances explainability and helps us better understand the model's behavior. While previous methods like RT trajectory and hamster offer some steering capabilities, they are limited by their design and training approaches. In contrast, MolmoAct can adapt its steering to new spatial configurations and ambiguous instructions, providing a more flexible and user-friendly control interface. Lastly, we discuss the concept of chain-of-thought prompting, which has improved reasoning in LLMs across various fields. This idea has been applied to robotics, where models like ECOT and COT-VLA have explored reasoning in embodied tasks. However, unlike these models, MolmoAct grounds its reasoning directly in the scene, allowing for clearer visualization and improved action prediction. This spatial grounding enhances our understanding and effectiveness in robotic manipulation tasks.